If you were asked to describe how large the room you're currently in is, you'd be able to give an answer with a fair amount of confidence. Or, in another scenario, you can easily tell if a car is driving up behind you, even without being able to see it. The fact that you can eyeball or just know where something is an extraordinary fact. How do we really know where things are? When we look at a lamp on a table, we know in our heads that the lamp is somewhere in the universe. But notice, we always describe where things are in relation to one another. The books are on the shelf. Turn left at the corner and walk until you see the fire hydrant. How we describe where something is completely depends on whose perspective you look at it from. My left is your right, and my right is your left. This is why we have to agree on a frame of reference, a ground truth on how to perceive the world. The vast majority of our life, we interact with objects that we can directly see and use. We use people-sized tools to do people-sized things. But how do you measure something bigger than yourself? The answer is one ruler at a time. As long as we create something long enough, or can break it up into multiple segments, we can understand something in people-sized chunks. It seems like our original mystery is solved. We know where stuff is because we can measure distances between objects and their relation to some ground truth. This fits all very well with our perception of our everyday world. This leaves an important question unanswered. How do you measure something you can't possibly reach or even see? When I phrase it this way, it sounds like an impossible task. I can't just take a ruler and measure the distance between me and the sun, but we know it's possible. I mean, how else could we know such a thing? In fact, it's not as difficult as it may first seem, and it has a little to do with skipping rocks. Let's try answering a different question to gain some insight. If I were to take one of these rocks and chuck it into the pond, how could I know where it landed? At first, this may seem like an equally unhelpful problem, since we know nothing about how the rock was thrown, but the key is actually in the ripples. Let's look at the same problem from a bird's eye view. However, this time we'll be on a boat in a lake. Point A. Someone then throws a rock, and it ends up here.
As of right now, it's impossible to know where it landed, but notice the ripples take time before they can reach you. The ripple has a velocity. We all know the formula for speed, which is simply velocity equals distance over time. Therefore, if we know how long it took for the wave to hit us and how fast the wave travels, then the distance traveled would be distance equals velocity times time. We know the speed of a pressure wave through water, but don't know how long ago the rock hit the water. This seems a bit discouraging because we're still missing some information. But for the sake of this experiment, let's try adding more people. Let's say 2 people row a boat to 2 predetermined locations in the water, PA and PB. Since we know the locations of each person exactly, we know the distance between them, DF. But before we leave shore, each person starts a stopwatch to keep track of the elapsed time. Once they are in position, another person somewhere throws a rock into the lake. Notice, whoever is closest to where the rock splashed will see the ripple first. So PB starts his stopwatch and stops it at time equals 15 seconds. Then 5 seconds later, PA sees the ripple and stops his stopwatch at 20 seconds. If we freeze the moments in time when person A and person B saw the ripple, we can see that the distance from A to the rock is the orange line. And likewise, the purple is the distance to person B. The problem is that B and A don't know how far they are from the splash's center. But hidden in plain sight is some extra information that we didn't have before. We know exactly how long it took for the wave to travel from person B to person A. And so therefore, using our distance equation, distance equals velocity times time, we know how much extra distance the ripple had to travel. This diagram looks eerily like a right triangle. Using a bit of trigonometry, the cosine of theta is known as the adjacent divided by the hypotenuse, the adjacent being the extra distance, change in time times velocity, divided by the hypotenuse, which is the distance between the two people. However, using a right triangle, we made a massive assumption. Is this really a right triangle? What if in another case the ripple was received so that the right triangle is a terrible approximation? And as we look at the picture, the circle's curvature intrudes onto the triangle's area in this case. However, this actually isn't that big of a deal because as the radius of the ripple increases, along any two close together points, the outer edge of the circle looks flat and can act as the sides to one of our triangles. You can also decrease the distance between the 2 points. However, the time delay of the ripple decreases, which would require more accurate timing. That's the gist of how to find the origin of a wave. This method is known as the time difference of arrival. We take advantage of a wave's slowness to measure the difference in time and estimate the direction it came from. The really cool thing is that the more people you have, the better your estimate becomes. You can locate the exact position of a point in space if you can measure enough time delays and determine the intersection of different rays, where those rays come from the headings found from each of those triangles. And now you might be thinking to yourself, wait a second, aren't there really 2 triangles that correspond to every time delay? I mean, we have the same distance dm and the time delay distance, which would mean we wouldn't know if the wave came from forwards or the backwards direction. And this is true for any direction the wave comes from. How people hear is a direct parallel to figuring out the origin of ripples in a lake. Your ears convert air pressure waves into electrical signals, and the brain figures out the time delay to then know what direction the sound comes from. This is also how surround sound headphones trick the brain. Your headphones artificially adjust the time delay between multiple speakers so that you think that sound is coming from a specific direction. And that whole issue of not being able to know forwards from backwards is still a thing. You might not believe me. Of course you can tell if a sound is coming from behind you or in front of you, but your brain has one trick up its sleeve that allows it to bypass this issue. Without this trick, we'd have to deal with what is known as the cone of confusion. When we drew the pictures of the 2 triangles, that was only for the 2-dimensional flat world case. When you step into 3D, there are actually an infinite number of triangles that would arise. You can imagine rotating a right triangle about an axis to then create a cone. As a result, any point along this infinitely long surface of the cone could possibly be a sound. So how can we know if the sound comes from in front of us or behind us? One of the primary reasons is due to the shape of the outer ear, known as the pinna. It has the shape it does, so the properties of a sound wave get modified based on what direction it bounces off the ear. And it's not just our ear. The brain interprets how the sound hits every part of our head, including the ears, nasal, and oral cavity. How the properties of the head modify the sound is known as the head-related transfer function. If you thought it was weird that we can measure and know stuff about waves that we can't visibly see, it's even weirder when the waves pass through the fabric of reality. LIGO, the Laser Interferometer Gravitational Observatory, was constructed to measure gravitational waves from cosmic events like 2 black holes spiraling in towards one another. Black holes are such massive objects that they warp space-time and can create gravitational waves. The wave isn't passing through the air or water, but is stretching and compressing our entire reality a tiny, tiny amount. So how could you possibly measure something like this if reality itself is stretching? The main idea is relatively simple. Imagine that we have a laser shooting out and hitting a sensor. Light, like anything in this universe, isn't instantaneous. It has a velocity, c, which is the speed of light. It takes time for light to travel from the laser to the sensor, and in theory, if you have a distance that never changes, that is traveled by speed that never changes, the amount of time it should take to travel should remain the same at all times. However, what if reality slightly expands so that the distance between the sensor and the laser increases? the time it should take for the light to travel should be a tiny bit longer. The LIGO experiment uses what is called a Michelson interferometer to measure gravitational waves. They shine a laser through a beam splitter so that half the laser beam travels upwards and the other half travels straight. In both directions, the laser passes through a set of mirrors called the Fabry-Perot cavities. This basically causes the laser in each direction to strengthen significantly by bouncing the light back and forth until it hits a critical number of bounces, over 300 in this case. This much stronger beam emits from the double mirrors and bounces back to the center beam splitter. You'll see that the two laser beams, when combined, actually disappear. It seems a bit crazy that light can just disappear like this, but this is actually due to the wave nature of light. Light has a frequency and amplitude, and so if one beam of light is perfectly out of phase so that the peaks of one line up with the valleys of the other, when combined, you get complete destructive interference. No beam ends up showing up. And that's what we expect to happen when nothing funky is happening with gravitational waves. The beams should cancel out. However, when reality slightly expands in either the x or y direction as a result of a gravitational wave, this results in the beams of light being slightly offset from one another. And when those offset beams are combined, the result is a faint resulting beam detected at the output of the beam splitter. Pursuing such a project like LIGO, while really cool, is a really expensive endeavor. Physics is absolutely necessary, but not cheap. It is an insanely complex system because it's looking for gravitational wave perturbations on the scale of 1/10,000th the width of a proton. It's so sensitive that cars in nearby roads and earthquakes across the world can affect the measurements. Each of those legs jutting out of that building in the picture, where the beam splitter is housed, are 4-kilometer vibrationally isolated, vacuum-conditioned tubes that the laser bounces back and forth through. The construction of this was completed in 1999 and still operates today at a total cost of over $1.1 billion. And not to knock on LIGO, but there's a really cool project that I found out about while attending a space research symposium. NanoGrav, known as the North American Nanohertz Observatory for Gravitational Waves, is an alternative method for searching for gravitational waves. And I feel like their method is really clever. They take advantage of these things called pulsars, which are the remnants of a much larger star but collapsed down to a neutron star. What makes pulsars special are their periodic rotations. Pulsars also emit massive magnetic fields that are detectable from Earth. And because the pole of the magnet is not directly in line with the rotation of the pulsar, this creates a lighthouse effect where the rotation of a pulsar shines onto the Earth every now and then. There have been thousands of different pulsars discovered, but only a few of them spin more than 100 times a second. These pulsars spin at a highly regular rate, and so by constantly checking for deviations in the timing across pulsars, you should be able to know if a gravitational wave passed through. This is because the gravitational wave expanded space, resulting in slightly more or less time for the magnetic reading to reach our radio telescopes. And to add onto the coolness factor, the more gravitational laboratories there are available on Earth, the more accurately we can pinpoint the origin of a wave using the time difference of arrival, just like the rock hitting the pond. While most of us do not have a radio telescope in our backyard, I feel like NanoGrav makes this kind of science slightly more accessible to all of us. And I think the key takeaway from this video is that it doesn't always take $1 billion to figure something out, to measure something that you can't see. A little clever thinking can take you very far.